Thank you very much. Hello, everyone. So, yes, what we're going to be talking about is how difficult it is to analyze GitHub data. But let's just set up the problem. Let's just imagine that you work in some company and you have to pick a programming language. What language shall you pick? And what are the impacts of such a choice? So we know that choosing a language is tricky because once you have picked it, you're stuck with it. So you may as well try to pick the best language there is. Problem is, what is the best language? We could say maybe the best language is the language that has the fewest bugs. All right? What is the language that has the fewest bugs? We can't do a large-scale study with humans. You know, that's probably impractical. So what can we do? Well, one thing we can do is look at the largest source of programming information we have, which is GitHub and GitHub histories. And this is what I'm going to tell you about. So in 2014, there was a paper that was titled A Large-Scale Study of Programming Languages and Code Quality on GitHub. And that paper tried to address the question, what is the best programming language, through the proxy of bugs. And what the paper did specifically is answers 4 research questions. I'll just mention the first one because that's the one that's the easiest to think about. And first one says, are some programming languages more defect prone than others? And if we can answer yes, and if we can identify these languages, then we have a hint as to where to go when we select our next project language. All right, so what did the authors do? Well, they did a study, and the study went sort of like this. They gathered 800 projects from GitHub written in 17 languages. They split the projects according to files. Files large, that have fewer than 20 commits, or projects that had fewer than 20 commits were filtered out. Then every commit was labeled either as this commit fixes a bug or it doesn't. And then we used that data to do a regression and try to infer the trend for each programming language. And the results they came up with are shown in this table. So yes, this is too small to read. It lists 17 programming language. The coefficient here, when positive, means the language is associated with more bugs than the average. And there are p-values here that tell us whether that particular line is statistically significant. Since this is too small, let me simplify. The study came up with a bunch of good languages, right? These are languages that are associated with fewer bugs, and you know, for us in programming languages, that kind of makes sense. They are the godly languages, functional, typed, life is good. Then there was a batch of meh languages, languages that are were either statistically not significant or didn't have much from the, didn't deviate much from the average. And then you have your bad languages. And the bad languages are pretty much as you would expect. So for those in the back, it's PHP, C, C++, and Objective-C. All right. So they did this. We read the paper, and you know, the paper was fine. It's got, you know, good reviews and all. But there was one small sentence buried in the middle that kept bugging at me. And this was the sentence. In the middle of the paper, they had this sentence that said, Google's V8, a JavaScript project, was responsible for all the errors, blah, 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 blah. Yeah, right. What? Okay, so we had the same feeling. And, you know, to cut a long story short, since this is a 20-minute talk, I'll skip to the part where we obtained the data from the authors, and we tried to conduct a reanalysis of their work. So what is a reanalysis? Basically, the original study starts from the real world, obtains data, applies statistics, and reaches conclusion. Well, every one of those steps will be reanalyzed. So we will validate data acquisition, we will validate data cleaning, and we will validate the data analysis. If after validation we reach the same conclusion, we can sort of say that probably the results are true, or at least we have increased our faith in the results. So what I'll do, the paper that this comes with has a lot more details. What I'll do is just give you the Cliff Notes version in 7 steps. So first step, so this is table from the paper, and what it lists is programming languages and the 3 largest projects in each programming language. So I'll just pick out a few. Linux, 17 million lines of code, solid piece of engineering. WebKit, 3 million lines of code. Haskell, PenDoc, 19,000 lines of code. Remember, these are the largest project in their corpus, right? Every other project will be smaller. Scala, 61,000 lines of code for the Scala compiler. And Rails DevBox. So these are the 3 largest projects, and what we're to believe is that this is representative of, you know, average behavior. So here I'm plotting a line which has the number of commits, thousands of commits, and the number of bug fixing commits. This is the median, and you can see there are languages with very few commits, and hiding at the edge here is C, because of Linux, has lots of commits and lots of bugs. Now we're to expect to believe that we can draw conclusions that apply as well to this as to that. Maybe we can. Let's see. So second step. So there's a lot of effects that we believe we're not fully controlled for. So, you know, one kind of effect is that 10% of the developers accounted for 50% of the commits. And actually, more than that, the paper confused committers and developers, which, you know, if you know GitHub, is not the same thing. Some tasks may be more bug-prone than others. So if you have more systems projects, maybe you'll have more bugs or different bugs. Some projects may be commercial, some projects may be open source. There's a long list in the paper of things that were not even considered by the study. We can't control for them, but, you know, we know they're there. This picture, what it shows you is over the lifetime of a bunch of projects, so this is the Scala compiler, this is Linux, the rate of bugs. And the rate of bugs is flat in Linux. You always have the same number of bugs. But for some projects like Homebrew, over time, the number of bugs increases. And I don't know, so the Salt project, as time goes, the number of bugs decreases. So the rate of bugs changes. This is not controlled for. Does it matter? I don't know. So there are things we couldn't really correct. But there are other things we could correct. So remember, these are this table. So I said that this is WebKit up there, and there's Bitcoin. There's WebKit again. There's Bitcoin again. So in the biggest project, we're double counting some of the code. Why are we doing that? Because they use GitHub stars to select the project they included in the study. Just pick the project that has the largest number of GitHub stars. Which means that, in particular, they included 17 variants of Bitcoin, right? And other completely duplicate. So 2% of the data, which is not huge, but it may still skew, is complete duplicates. So I said we would also validate data acquisition. So what we did is we tried to look at the projects that were included, and we try to find them on GitHub today and check that the commits that are in the data set are actually in the project. And that's actually more challenging than you'd think. So out of the 729 projects that they had, we could only find reliably 400. And for those 400, we found that they were missing about 20% of the commits. And this is a graph that shows for different languages the percentage of missing commits. And in case of Perl, 80% of the commits that are in GitHub somehow were missing from the study. Again, why? We don't know. Why? It is gone. So these are the kinds of bugs you encounter, right? Suddenly the projector goes away. And what do you do as a speaker? Not entirely sure. We will try to keep going flying blind. So what we found is there's a lot of missing data. Again, this is something we can't correct for, but it's certainly worrisome because that means they haven't addressed everything. Yeah, it's doing something, but not much. Nothing. All right. All right. So the suspense is killing the audience. Ah. Oh. Ooh. All right. Continuing with this story. So in the data set, we found that Typescript was one of the godly languages, and the data set had commits for Typescript starting in 2003 and going all the way to 2014. Issues? I like Wikipedia. It says, for the back, it says that Typescript was released in 2012. So how do we know that a file is a Typescript file? Well, we know that a file is a Typescript file because of the type extension .ts, and .ts happens to be also used by translation files in multilingual software, which are generally not buggy. So out of 41 TypeScript project, only 16 have codes, and the 3 largest one are just code definitions. They're type signatures. Again, likely to not have bug. So basically, the TypeScript data doesn't have enough data to do much. All right. Remember I said the thing that bugged me was V8 was tagged as a JavaScript project? Well, if we look in the data, it is a JavaScript project. It has 2,900 JavaScript commits, 488 Python commits, and the whole VM was written in 7 C++, big, large commits, right? So what happened? Well, most of the code we see is tests. They're the tests that come with the C++ code that was broken. So that we find. And they're buggy. Well, they're buggy in the sense that they're reporting on a bug. So yes, we will label them as bug fixing, but they're not bugs in JavaScript. And all C, CC, CPP, C++, CP, CXX, and .h files were ignored. The only extension that was used was .cpp. So generally, 16% of the file we found in the corpus were test files. Again, do we believe that bugs in test files are representative? Maybe. Are they the same as in code? Probably not. So, now we get to statistics. Statistics. So, remember I mentioned something about a p-value? So what is a p-value? It tests a hypothesis. Yeah, whether it holds, not holds, what you've heard in your statistics class when you were sleeping. Well, the problem is we don't have one hypothesis. We have 17, because we have 17 different languages, or 16 if we delete TypeScript. So, and by the way, this is a common mistake in data-driven software engineering, says the 2018 ICSI paper that I cite there. So what do you do when you have multiple hypotheses? You have to adjust your p-values, basic stuff. So either you use Bonferroni, which is a very simple thing, you just divide by 16. Or if you want to be fancy, there is something called false discovery rate, citations available, but basically this changes your stats. Okay. All right, we're getting to the fun part. So the fun part is, you know, what is a bug? What is a bug? Well, what is a bug? What is a bug? What is a bug? So how do we find that something is a bug? Well, we'll automatically read, because we have 1.5 million commits. We automate this. We automatically read the commit message, and we find that this is a fix. Fix is a bug, right? Right. So we fix the comment. Now we find that the occurrence of default. Default has fault embedded in it, so that's probably a bug. On the other hand, clauses number 153 is not a bug. So this is what the tool reports. Why? Because they grep for a series of keywords, which is, citation by some of the authors, not a good idea. I mean, they wrote it themselves that you shouldn't do this. So we asked a bunch of software engineers to evaluate a sampling of the commit messages, and we find that the automated method 36% of the time was wrong when it said something was a bug, and 11% of the time was wrong when it said something wasn't a bug. So basically, there is data in there, but it's hidden in this noise. All right, so we can use statistics to correct for it. So we can use the bootstrap method, see the paper for the detail, and we get a new notion of what is statistically significant and what will happen. So this is the table, and in this table I have the original, and each of our steps of cleanup is listed, and I'll just simplify this by saying C++ used to be statistically significant, it isn't anymore. Objective-C used to be statistically significant, it isn't anymore. JavaScript, it isn't anymore. Typescript, we don't have any data. PHP, not statistically significant anymore. Python, not statistically significant anymore. Scala, not statistically significant. And then I'll remove all the languages that were already not statistically significant in the beginning. Sorry, I remove Perl because we have so little data that it's not worth bothering. And then all the yellow ones are the ones that weren't meaningful. So what that leaves us with 4 languages, right? C++, Ruby, bad. Clojure, Haskell, good. Right? So typed languages are good, like Clojure. Yeah. This is not saying much. But it's still better than it's still worse than you think. Because statistics again. P-values should not be used with large data sets. Because the properties of p-values is as the data size grows, the p-value mathematically will become small. Citations. The statisticians have been telling you not to do this. Quit with those p-values. They're not useful. I have the citations are on the paper if you care. So what do? Well, you want to capture the effect size, right? So what can we do to capture the effect size? What we're going to do is we'll take the language that has the most bugs, the language that has the least bugs, and we'll try to see if you can tell them apart. So this is the graph, and the way you read this graph, so I picked C++ and Clojure, best and worst, and this is imaginary project. As you grow the number of commits, the likelihood of bugs. So these are bugs, these are commits. So for instance, here I have 600 commits and 200 bugs for C++. And the point I want to make is these overlap. The only places where we can tell apart C++ and Clojure are in this small band below or in this larger band above. But basically, it's the best language and the worst language, according to their data, are indistinguishable. And I'll leave you with one last thing, which is last week what I did, because there's still, even if they did everything right, I still have a feeling that you wouldn't get what you want. So I went to two projects, one in C++ and one in Clojure, and I manually tried to calculate how many bugs are affected by the choice of language by just looking at the code for each commit. And I found that only 6% of the bugs in C++ and 5% in Clojure are language bugs. So what that means is there's very little signal, right? And we're trying to make statistics, but there's so little signal, there's so much noise. We'll never get anything meaningful. How much do I have?
Like 1 minute.
Okay,
2 minutes.
perfect. So we've gone through the 7 sins of analyzing GitHub data. I'll leave you with something else, something that I think all of us should really pay attention to. So the story is this paper was accepted at FSE. People liked it a lot. Then it was forwarded to CACM. People liked it a lot. It was published as a research highlight. Then a conversation started in various forms of media, right? The shocking secrets about static types, less codes, less bugs, statically typed functional languages win, and just boom. Okay. So what's going on here is the way people read the paper, they didn't read the paper as we have found an association between bugs and languages. They read it as languages cause bugs. But the authors didn't say that in their paper. They said some languages have a greater association with defects than others. They said the right thing, except it's buried in the paper, and the paper is all, sort of geared towards, it's like clickbait, right? It's geared towards making you think that the conclusion is causation, not correlation. So we did, we wanted to see how the community perceived this work. And we did a meta-analysis of the citations. And roughly what we found is that most of the citation of the work, 77, are shotgun citation when you have a long list. People said nothing. 12 of the citation were just saying, oh, this is the method people have used. And then there were only 2 papers that said this is a correlation. The majority, 24, jumped to the conclusion this is causation. And out of those 24, 3 here are papers by the authors. So themselves, they got trapped by this. So the point is, we have to be super, super careful. If you write something, your responsibility is to get the reader to understand what it is you have done. And I claim that they didn't do this. So I will conclude here. Thank you very much. And yeah.
Thank you. One question as we transfer to the next speaker. By the way, this was a paper submitted to Topos, I believe. So you also can try the route of submitting to Topos. And if you have a new paper submitted to Topos, it can be presented at NUXLA or another SIGLAN conference.
And the paper was rejected by FSC and XC.